got the derivative of tangent. So we obviously did sine and cosine already. So the derivative formula for the tangent curve. Now, first of all, remember what the tangent curve looks like? Yes? Okay, with some asymptotes. So there are some places where this derivative will be undefined because there are some places where the tangent curve doesn't exist. What do you notice about the derivative of what the derivative of tangent will always be? As long as it's defined, yeah, it always will be positive. I don't think I've ever really made that realization on my own before, but yeah, the slope is always positive. So the derivative of tangent will always be positive, and this is just something you're going to have to memorize. But now that I think about it, of course, it is always positive because the derivative of tangent is secant squared x. Because it's squared, it will always be positive. Follow? Okay? So that will come up now. You have to memorize that. Actually, just while I'm thinking of it, in front of your textbook, there's a whole list of the derivative rules that you have to know. Some of them we already did. Here's just, u is like the function, so if there's a constant out in front, the derivative is just going to be the constant out in front. We've been doing that. Here's your product rule. U times v, first times derivative of the second plus second times derivative of the first. Here's your derivative of any constant, 0. Here's your derivative of just a linear x, that's just 1 because that's the slope. Obviously we haven't done any natural logs or logs, but sine we've done. Derivative of sine is cosine. We'll talk about this u prime thing within the next couple days. Derivative of tangent is secant squared. Over here, the derivative of the sum is just a derivative of each piece, so we do that on a daily basis with the power rule. Here's your quotient rule. Here's your power rule. We haven't done absolute value. Here's your e to the x is e to the x. Again, we'll talk about this additional u prime shortly. Derivative of cosine. So there are a boatload of rules that we'll continue to thread into this. Josh? Secant squared is 1 over cosine squared. Just cosine squared. Yep, secant is just 1 over cosine, so secant squared would be 1 over cosine squared. So that's the actual answer, but then with this activity up top, I wanted you to find the derivative of the tangent function, so pretend like I didn't tell you that. By first rewriting the tangent as sine over cosine. If you were to find the derivative of this using the quotient rule, the derivative would be the bottom times the derivative of the top, and the derivative of sine is cosine, minus the top times the derivative of the bottom, and the derivative of cosine is negative sine, all over bottom squared. So that would be, let's see, cosine squared plus sine squared all over cosine squared. And your Pythagorean identities tells you that cosine squared plus sine squared is 1. So that's just 1 over cosine squared, which is secant squared. So there's really your proof based on what you know about sine and cosine and their derivatives and the quotient rule as to why the derivative of tangent is secant squared. Good? All right. So we're just going to practice it. First example, more of this product rule. So I'd first rewrite the function x to the 1/3 power, x to the 1/2 plus 3, and I'm just going to follow the product rule. So my derivative is first times derivative of the second plus the second times the derivative of the first. Now, what is the derivative of x to the 1/3 power? Let me go with Haley. Not to the negative 1/3. It is 1/3 x to the. What do we do to the exponent, Haley? Subtract what from it? 1. So 1/3 minus 1 is like 1/3 minus 3/3, which is negative 2/3. So that's interesting. Could be. Even still, you're going to have an x to the 1/3 power times an x to the 1/2 power, so you're going to have to do some adding of exponents that are fractions, get a common denominator. So you could. From here, that would be the cubed root of x would stay up top over 2 root x. Plus, this would stay up top on the second term, so root x plus 3 over 3 times the cubed root of x squared. Now, in the back of the book, you might have noticed last night that a lot of times when it was the sum of two fractions or the sum of a fraction and a whole number, they got a common denominator. So what would that look like here? I'm trying to think if they would do that or if this is too messy. Because right now we have right now, let's just do it. X to the 1/2 power versus this side is x to the 2/3 power. So maybe we could just get them both to be just x. What do you think about that? And then 6. Can we do that? So to get this to be a 6, this would need a 3 and another root x. Yes? Root x, root x. And to get this one to be a 6, this one would need a 2. What would this one need to get that to just be an x? Because currently it's x to the 2/3. So it would need x to the, what would you have to multiply x to the 2/3 by to get it to be x to the first power? Just 1/3, right. So that would be the cubed root of x. So in doing that, now, again, so back to what Josh was saying before, in order to multiply these, I would have to get the, like, x to the 1/2 times x to the 1/3. I would have to get that common denominator. What is 1/2 plus 1/3? Adding exponents. That's 3/6 plus 2/6, so is that 5/6? Over 6x plus, and over here I'm going to have to distribute. So again, that's x to the 1/2 times x to the 1/3. Oh, I forgot the 3. Yep, you're right. Sorry. So up top over here, it'll be 2x to the 5/6 plus 6 cubed root of x, or x to the 1/3 if you want, all over 6x. I'm hoping that the back of the book is not going to make you go through this. So if you add your fractions now, it's just 5x to the 5/6, which could be written as radical 6th root of x to the 5th, or exponential, plus 6x to the 1/3, all over 6x. I'm going to go ahead and say they're probably not going to do all that. But it was fun, just for fun, we did it. You'll have to take a peek and see if they do that. If they do all that, then Josh is right from the get-go. It would be easier to just do that common denominator situation once and just do the power rule. All right, second one. What's different about this? Right. So You could do like, and just bear with me here before we start and decide. We could treat this as the first, and this is the second. So you could do the first times the derivative of the second, plus the second times the derivative of the first. However, if you're doing the derivative of the first, that in and of itself would require a product rule. Yes? Just the derivative of this chunk. So you would be doing a product rule within the product rule, which can get awfully confusing. So if we can avoid that, we would want to. So I would recommend multiplying these out first. So that would be x to the 5th plus 2x cubed minus x cubed minus 2x. And then just combining like terms, that would be x to the 5th plus x cubed minus 2x. Now the product rule is still long, but it's not as confusing. You don't have product rules within the product rule. So your first times the derivative of your second, 2x plus 1, plus your second times the derivative of your first, 5x to the 4th plus 3x squared minus 2. So your cleanup here is going to be 2x to the 6th plus x to the 5th plus 2x to the 4th plus x cubed, when I distribute my x cubed, minus 4x squared minus 2x. And then I have another trinomial times a trinomial. So you just have to be very careful with all of this. So I'm distributing my x squared through, which will be 5x to the 6th plus 3x to the 4th minus 2x squared. Then distribute my x through. So that's going to be a plus 5x to the 5th plus a 3x cubed minus a 2x. And then your negative 1 through. So minus 5x to the 4th minus 3x squared and plus 2. Ugh. All right, combine like terms. No. I don't think I ever force your hand. Like, not with one like this. Yeah, no, because the majority of these, just for the sake of grading purposes, are going to be multiple choice. So, unless it was an open response. I'll take a look and see on the test that I just wrote if I did that. I don't really remember. 7x to the 6th. How many x to the 5th do we have? 1 plus 5 is 6. 6x to the 5th. And then to the 4th, we've got 2 plus 3 is 5 minus 5, so that's gone. No x to the 4th. X to the 3rds, we've got 1 plus 3 more is 4. I'm just crossing them out as I account for them so I can tell if I missed anything. Minus 4x squared minus 2x squared is minus 6x squared. Minus 3 more is minus 9x squared. Minus 2x minus another 2x is minus 4x plus 2. Ugh. Any questions besides ugliness? Okay. This one gives us a function that's a quotient. So we're going to use the quotient rule here. But also note that C is a constant, which should make things better for us. So if we're doing our quotient rule, our bottom times the derivative of the top. Ellie, what's the derivative of the top? Liam, help her out. Just negative 2x. Explain, Liam, why you don't have the 2c in yours. Right. C is a constant, so c squared might as well be like 5 squared, 25. That is a benefit to us because when you take the derivative of a constant, it's 0. So your derivative of the top is just negative 2x minus your top, which is c squared minus x squared, times, Ellie, try again. What's the derivative of the bottom now knowing what you know? Just 2x. Good. All over bottom squared. Oh, yuckies. All right, so the cleanup for this is going to look like negative 2c squared x when I distribute. I'm just putting that c squared out in front of the x because it is a constant, so it would be more in the coefficient section. Minus 2x cubed. And on this next one, I'm essentially distributing a negative 2x. So minus 2c squared x plus 2x cubed. All over your denominator squared. In your numerator, the negative 2x cubed, positive 2x cubed cancels. The negative 2c squared x minus 2 more c squared x is going to be negative 4c squared x. And that's that. And then this last example has a secant, and I didn't give you the derivative of that yet, but here are the rest of your trig derivatives. So the derivative of tangent is secant squared. We did that, and we proved that up top. The derivative of secant is secant tan. The derivative of cotangent is negative cosecant squared, and the derivative of cosecant is negative cosecant cotangent. Yes, you have to know those. So we'll obviously use them enough where some of them will sink in. Sine and cosine already, do you feel like you had to memorize those, or you just naturally memorize them because we've used them so much? But I guess the tangent and the secant one, just to help you kind of chunk the material a little bit. The tangent and secant one are closely related, and the cotangents and the cosecants kind of use each other. So I kind of would chunk those two with the secant-tangent relationship, and these two with the cotangent-cosecant relationship. That being said, the ones that are the tangents that you're taking the derivative of, whether it's the tangent or the cotangent, that's the one that turns in just the squared. Versus when it's the secant and the cosecant, you are kind of turning it into a product. And then these two obviously have the negative involved. So if we, again, you just have to memorize those. There's no real way around it. On this particular one, if we are finding the derivative of h of x, I think I would first make this x to the negative first. And so that h prime of x would be power rule on the first term, negative 1, x to the negative second. And then just a trig rule here. The derivative of secant is secant tan. So that would just be minus 12 secant x tan x. Cleaned up, that's just negative 1 over x squared minus 12 secant x tan x. Any questions so far? Jalen. Oh no, that's definitely, if it was multiplication, you would either need a multiplication symbol right here or parentheses. Yeah. Anything else? All right. On the back, on this first one, what do you make of the first term? What's the derivative of that? Or like Michelle, what would you do for that one? Just focusing on the derivative of the first term. What rule would you have to use? So just x cosine? Someone help her out, because that would not be the correct. What is she missing, Jalen? Right, you have to do the product rule, because, so there's a difference here. If you're asked to find the derivative of 5 sine x versus x sine x, this is a constant. So our derivative rule says that y prime is just that constant out in front of the derivative of sine x, which would be cosine x. Because x here is a variable, that introduces the two different functions, where it would be the product rule between x and sine x. So the first times derivative of the second plus second times derivative of the first. Does that make sense? Okay, so if it's a now, by the way, if you wanted to do the product rule with this one, you could, because your first would be 5 times derivative of the second would give you this, plus your second, sine x, times derivative of the first, though, because it's a constant, is 0. That's why we get to ignore that, right? Maybe technically deep down within that, they are doing the product rule, but because it's a constant, that derivative is 0 and it cancels out the other terms. So the shortcut is, if it's a constant, just keep the constant out in front. But if it's a variable, you've got to use the product rule. So that would be the first times the derivative of sine is cosine, plus the second, sine x, times derivative of the first would just be 1. So that's the derivative of just this piece, plus the derivative of cosine is negative sine. So all in all, this becomes x cosine x plus sine x minus sine x cancels. So y prime is just x cosine x. Okay, and our last one here, evaluate the derivative at the given point. So, first thing I want you guys, this is just so you know, because it hole punched through it, obviously. F of x is the sine x times sine x plus cosine x is what that says in parentheses. So take a minute on your own and find the derivative. Okay, find the derivative of the function. And we'll see where we all land once we're done with that. Raise your hand if you're just stuck. Raise your hand if you need more time. Okay, I'll give you a couple more minutes. All right. Oh boy. Let Winter pick 3 numbers. See. Okay, it looks like this person's answer for their derivative ended here, and then they went ahead and they evaluated. Shoot, where's my pencil? So y prime equals. Raise your hand if you got that same answer. Ooh, good. So let's not look at that one, assuming it's right. Let's look at this person's. This person looks like they're not done yet. But it also... Oh, yeah, they are done. They just kind of look like they thought they should be able to go further. Whose is this? If you could go further. It kind of looks tempting because you have sine squared plus cosine squared sitting in front of you, but that's not a positive sine squared, so it's a... Yeah. So you, unfortunately, you can't. So you're good. So that's it. That's that. And then this person isn't obviously done yet. Let's see if they just aren't done yet or if they made a mistake. So take a minute to review this. Mistakes, so we'll play teacher, give away bonus points. You're not going to tell me mistakenly, you're going to pick a number. Video, by the way. Not that you care, it's just kind of funny for anybody who watches it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Ethan McMillan. Where? Be more specific. You want to go up to the board and show? Go up and show. So hard. So hard to say, oh yeah, right there. Okay, so they had that part right. It was just that first part. Okay, you can erase it. Good. So they did the derivative of the first times the derivative of the second plus the second times the derivative of the first. So all of this is good. They just should have left this alone. It's the first times the derivative of the second plus second times the derivative of the first. Good job, Nathan. Okay. All right, so I'll just go through the cleanup just in case people didn't get that far. Josh? Oh, you could use a double angle. You definitely could. You don't have to, but again, that would be a great thing to see at the end of, if you look at the answer in the back of the book and they have sine of 2x, that's our double angle formula. Good catch. Sine of 2x minus sine squared x plus cosine squared x. So in that case, some of these may turn into like an identity of sorts, like where you're trying to keep manipulating until you get that answer. That's your target. And same on a multiple choice. You end here, but that answer is not available. You'll look through your solutions, see that one looks similar, and then realize that that is the double angle formula. So first times derivative of this, what's happening here? This is yours, Alyssa, right? So you distributed. So you had to do your product rule twice. That probably was not efficient, huh? Does everyone see what she did there? So she did and rearranged her initial one and distributed her sine x. So here she had to do the product rule, first times derivative of the second plus second times derivative of the first, plus she had to do it again. Versus if I look at this one, this person just jumped right into it. The first times the derivative of the second is derivative of sine is cosine, derivative of cosine is negative sine, plus their second times the derivative of their first. And then they distributed sine x cosine x minus sine squared plus sine x cosine x plus cosine squared and combined like terms. Awesome. Okay, so I'm going to pass these two back, and then I'm going to piggyback. Is this you, Jalen? Whose is this one? Oh, yeah, Lily. I didn't take yours today. Can you pass those back, please? So from here, evaluating is just plugging in that pi over 4 minus sine squared of pi over 4. So 2, the sine of pi over 4 is root 2 over 2. The cosine of pi over 4 is root 2 over 2. Minus the sine of pi over 4 is root 2 over 2, but we're squaring that one. Cosine of pi over 4 is root 2 over 2, but we're squaring that one. So we end up with, this is 2 fourths times 2 is 4 fourths. Minus, when you square this, you get 2 fourths. Plus, when you square that, you get 2 fourths. So the minus 2 fourths and the plus 2 fourths cancels, and it's just 1. So if we were to look at this function, the slope at pi over 4 is 1. Okay? Just, I want to reconnect that to the beginning because it's easy to lose sight of what the heck it is that we're doing. We are finding the slope of this curve at pi over 4 when you're evaluating the derivative. Good. Any questions? All right, so your homework is there at the bottom, and